Hey guys, welcome back to day 39. We're talking about the first law of thermodynamics today. Thermodynamics was developed initially to investigate the process by which heat could be converted into useful work. So our goal is heat to work. That was the original lens of this whole area. And we're going to break it down into the actual reactions. We care about reactions and a reaction. So a reaction. We have reactants that react. How they react, we don't cover that, but we know they react and products are formed. We know that in reactants, bonds are broken and the products have new bonds formed. That kind of makes sense. And so a chemical reaction is a rearrangement of atoms and a redistribution of electrons. The law of conservation of mass definitely applies. So when we do this, when we look about heat to work, we're typically looking at a reaction that produces heat. We'll dive into that later. And so when we talk about energy involved, there are several. Sometimes there's light, right? So we got photochemistry. You got electrochemistry. We're mainly going to worry about heat and thermal chemistry. We're going to focus on heat. We're going to define heat and whatnot. So now there's two terms that I want to define real quick. Exothermic and endothermic. Exothermic means heat is released, heat out. And endothermic means heat is absorbed or heat in, right? Just like an exoskeleton versus endo, right? Endo and exo. Exo out, endo in. So heat's coming out, heat's coming in. So we talk about energy, remember, energy is neither positive or negative. Heat is a value and it's either going to or from. It's either going in or out. Energy is like money. So it's $20. If you have $20 in your wallet, if that $20 leaves your wallet, it's negative to you. If the $20 comes in your wallet, it's positive to you. It's still $20 though. So it has a value. It's just the sign has to do with direction. The same thing is true with energy. The sign is just direction. So when we talk about energy, a lot of times we'll talk energy. There's two main types that you've learned about. You learned about kinetic and potential. So we talk about kinetic and potential. Kinetic was due to motion and potential position. So kinetic is the energy of the motion, and that is Ke equals 1/2 mv squared. Potential, usually in a physics class, we learn that potential energy has to do with the mass of the object, the acceleration due to gravity, and how high up it is, because we're going to talk about how high it is from the Earth's surface, so to speak. Chemical potential energy is the energy of electrons due to their positions relative to the nuclei. It's basically stored energy. Do these bonds have energy that we could actually, when they react and rearrange, the electrons get redistributed? Is there energy out? Does that redistribution of electrons and atoms result in lower energy for a new molecule or in a higher energy for new molecules and combinations? So when we talk about the first law of thermodynamics, we'll talk about, we find a system. And a system is a part of the universe under examination. So here's my universe. And my system will be inside of it. There's my system. So in thermodynamics, we're assuming that the universe is a closed system. That means there's nothing coming in, nothing coming out. No mass and energy or substances going in, no mass and energy coming out. As far as we know, that's a good approximation from what we can observe in the light sphere. So the system has E. This E is the internal energy of the system. Is the internal energy of the system. I can put energy into the system or take energy out. So the system, the universe, everything inside the universe that's not the system is technically going to be the surroundings. Now, if you have a campfire this upcoming weekend, is that going to affect anything on Jupiter? No. But technically speaking, Jupiter's part of your surroundings. So when we look at our system, whether you're having a campfire or whatever you're doing, how do you put energy into a system? How do you take energy out of a system? The question is how? How is that happening? And the answer is I can heat the system. So I can heat it or do work on it. Delta E is the change in internal energy. Delta E is a change in internal energy. So heat has a letter of Q. Work has a letter of W. Delta E then is going to be equal to Q, the heat, plus the work. Now, by convention, Q and W are positive if the heat and work increase the energy of the system. Going back to money, if $20 increases the money in my wallet, I consider it positive. If the $20 decreases the money in my wallet, I consider it negative. Same thing with energy now. If energy goes into the system, we're going to call it positive. If it comes out of the system, it's going to be negative. So let's talk about this system, this internal energy. A system possesses internal energy by virtue of molecular motion. This energy is a random or incoherent motion, often called thermal energy. Heating a system increases the incoherent motion of the particles in the system. Work is the result of an organized motion of the particles For example, a wind blowing or a gas expanding in a cylinder. So let's define the first law of thermodynamics. Which is the conservation of energy. Energy is neither created nor destroyed. The amount of energy in the universe is constant. If we look back here this picture, the universe, closed system, the system has internal energy, and I can put energy in from the surroundings or take energy out of the surroundings. Get a little circle there. That's the first law of thermodynamics. All the energy in the universe is constant. Let's recap some units. We recap our units here. Remember, force is mass times acceleration. F equals ma. Kilogram, meter, second squared. Or, that's a Newton. Force is a Newton. Energy and work have the same definition, so to speak, because they have the same unit, but they're different. They're very different. Again, energy is random motion. Work is coherent motion. So work is force multiplied by distance. So that would be a kilogram meter squared second squared, or a kilogram, I'm sorry, not kilogram, a Newton meter, which is a joule. So we have W equals FD. Also, W equals negative P times the change of volume, PDV, for expansion work. So work and energy, same unit. Also power, just so we get there, is energy or work over time, which is a kilogram meter squared second cubed, which is the same thing as a joule per second, or a capital W, which is a watt. Now, a little note, right? An older unit of energy is the calorie, and 4.184 joules is 1 calorie. Right? And by definition, a calorie is the quantity of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Also, 4.18, I'm sorry, that's the joules. 1,000 calories is a food calorie. So when we talk about energy transfer, we're mostly going to focus about, in this class, heat transfer. And in this class of heat transfer, the question is, how is heat energy measured? How is this measured? Right? How is heat transfer measured? And then the answer is in a device called a calorie, calorie meter. on calorimeters. Heat measure. We actually measure temperature change and then calculate the heat change. Well, what's temperature? Is temperature the same thing as heat? Is heat the same thing as temperature? Well, let's define heat. Well, let's first define temperature. Temperature is a measure of thermal energy. Right? Which is the motion, the kinetic energy of the particles. So temperature measures the thermal energy. How hot is this molecule? Heat is the total amount of thermal energy. It's the collective. So here's an example for you guys. Aluminum foil in the oven, 350 degrees Fahrenheit, about 177 degrees Celsius. You touch that 177 degrees Celsius aluminum foil at 350, and you can touch the aluminum foil with your hands, and you do not get burnt. As long as you don't touch the food, you don't touch the oven rack, you're fine, because the aluminum foil has a little mass and has a little bit of heat, even though it's a higher temperature than boiling water. But you get a little bit of boiling water on it, and it hurts a lot more than a little bit of aluminum foil. The reason is the water has more heat overall, even though it's at a lower temperature. Same thing with force. If my 4-year-old runs at me as fast as they can, and she hits me, not a problem. Bounces right off of me. All right? And let's say she's going 5 miles an hour. She could probably run that fast for a short period of time. A car hits me at 1 mile an hour. I'm going to be moving. Why? Because the car has a lot more mass, right? So just because the speed's not there, a lot more kinetic energy with the car because the mass and velocity play. Same thing with heat and temperature. So temperature is a measure of kinetic energy, of the kinetic energy or the thermal energy of the particles, and heat the total amount of that energy. And this leads us into energy, specific heat, and temperature change. So heat change, the change in heat. Is equal to the mass times this thing called specific heat times temperature change. So Q, heat change, equals M for mass, C for specific heat, and delta T for the change in temperature. Simply speaking, delta T is T final minus T initial. Heat change is measured in joules. Mass, most of the time, will be in grams. Specific heat is joules per gram degrees Celsius, and then temperature, it can be in Celsius or Kelvin. Most of the time, it'll be in degrees Celsius. So this specific heat This is the quantity of heat required to raise the temperature of 1 gram of substance by 1 degree, either Kelvin or Celsius. They're not necessarily degrees Kelvin, right? It's just kelvins, 1 Kelvin or 1 degree Celsius. This is an intensive property, which means it does not matter how much water we have. Our specific heat of water, liquid water, so H2O liquid, C is equal to 4.184 joules per gram degrees Celsius. There is something called heat capacity. And this is the quantity of heat required to raise the temperature of the system by 1 degree Celsius, or 1 Kelvin. And this is an extensive property because it does matter how much is present. All right, so heat capacity was used for when we talk about calorimetry in the next video. You might want to use the heat capacity of the whole system. Let's do 2 examples of this Q equals MC delta T. How much heat, there's your question right there. How much heat is required to raise the temperature of 50 grams of water from 20 degrees Celsius to 45? And it gives you the specific heat of water, 4.184 joules per gram degree Celsius. Q equals MC delta T. We're looking for Q. Right, how much heat? Q equals mass, 50 grams. Our specific heat, 4.184 joules per gram degrees Celsius. And then delta T would be 45 degrees Celsius, my final temperature, minus my initial temperature of 20. Ooh, I'm missing my decimal points. 20 degrees Celsius. That gives me a Q of 5,230 joules. Number 2, down here, how much will the temperature rise? So there's your question. You're actually looking for delta T here, kind of. How much will the temperature rise? If 1,000 joules of energy are used to heat a 10-gram block of copper, and it gives us the specific heat of copper is 0.385. Now, this is a good point to tell you guys that these values are in the chapter. So you're going to have to actually look at where specific heat is introduced in this chapter and actually look up the little table in the chapter. It's not in the back of the book. And again, I highly discourage you from using Google, because if they're off significantly, and either Pearson or myself won't take them if you're off. We might make our own stuff up too. You never know. So back to Q equals mc delta T here. We have 1,000 joules. And that decimal point means that there's 4 sig figs there. Equals my 10 grams. So I have 3 sig figs in this. 10.0 grams of copper. Multiplied by my specific heat of 0.385 joules per gram degrees Celsius. Multiplied by delta T. So delta T would be equal to 259.74, so 260 degrees Celsius. And that is the first law of thermodynamics. Hopefully that works for you guys. Take care, and we'll see you in the next video.